This is a schematic of a solid-state AC switch driven by two SCRs in parallel, back to back, and in between the two gates is a AC style of opto switch. And by controlling the LED on this switch, it connects the two gates together, and power then is passed through both SCRs. Back-to-back SCRs are kind of like a Triac, only you get two gates instead of just one. So we're able to put between the two gates an opto relay and drive it with DC. These SCRs come in really huge sizes. I have a couple that will do 110 amps AC through them if you put them back to back. These are common ones here. You can buy anywhere for a couple dollars. This optical relay I'm using here is obsolete, but here's one here that exists now that would work. It's a 4-pin instead of a 6-pin. But you got to make sure that the voltage rating for the switch side is well above whatever source voltage you're using on the AC. This is the SCR I've chosen to use in the test circuit. 4020 I'm using, that's a 20 amp version, and we'll be using two of those back to back. And it has pretty good specs here. Now I've used this particular one in most of my projects. It covers the 120 volts that I usually use as an input. The loads I usually have are no more than 300 watts. There's no heatsink required. Talk about that later, because the drop across these SCRs when they're conducting is really low. There's a lot of occasions where there's no heatsink even needed. So this will be the SCR I'm going to be using on the test circuit. Here's the SCR on DigiKey, and they're $2.88 a piece, so you need two of them. This is a low-cost optical relay that works fine in the circuit. I suggest if you're using 120 volts, get the 350 volt version. It's a DIP 4. It's the AQY210. They're pretty low cost. It will work great for driving the two gates of the SCRs. The LED drive current on this device is pretty low, 1.2 milliamps to operate it. A forward voltage of around 1.25. It's a pretty good optocoupler for this design and quite low cost. Here's the optical relay, and they're only $1.97, and this one would work fine on the 120 volt SCR solid state switch. This one's good up to 350 volts. You could probably even use it if you had a 240 volt AC input on the solid state switch design. Okay, I've got the circuit set up here on a little piece of vector board. Here's the two SCRs and the optocoupler. And we've got a 150 watt light bulb here. What I'm going to do is bias the LED with DC. We don't have the cleanest power coming in from the power line. It's kind of clipped at the top. That's the actual power line coming in. The other channel that's flat right now will be the output of the SCR switch. About 1.3, 1.4 volts DC. The light comes on and the switch is active. And we're at 120 volts AC. There isn't much difference between the waveforms from in to out. There's very little drop across the SCRs, even at 150 watts. So the circuit works pretty good. I've used it in a lot of different applications. And if I remove the DC voltage, we go down to practically 0 volts, pretty much 0 volts. You can come up with a circuit, I may do this later, for a zero crossing detector. So you can bring this up, have this thing turn on at zero crossing of the sine wave. Would be right here where you would turn it on. Either the rising or falling edge, doesn't matter. You could turn it on there, and that way there wouldn't be a big surge to your load and a big surge on the power grid. It would come up with the first cycle after the switch is turned on. So That's just with a 150 watt load on it. And the SCRs are very, very cool. So no heatsink needed. You can use power SCRs, really powerful SCRs, and use the same circuit to switch on and off the AC power. The input and the output together, and the waves right on top of each other there. So there's really no change to the waveform through the circuit. So it works out pretty well for this application.